we will introduce our next speaker. That's Dr. Jens Schmidt, who has a PhD in chemical engineering from the Technical University of Hamburg, as well as an executive MBA from Northwood University. He's a certified Six Sigma black belt and has 19 years of experience in the chemical industry with Dow in various roles. He's worked in engineering and manufacturing roles in different business units all around the world. And he's currently a corporate technology fellow at Dow, responsible for innovation, looking into sustainability, digitalization and such. Besides that, he's also a serial entrepreneur, also a founder of and owner of several startups and IT companies. And with that, I'll hand it over to you, Jens.
Yes, can you hear me well?
Yes, we can.
Okay, perfect. Thanks. Yeah, thanks for the invite. It's a pleasure to present about large-scale renewable methanol, and thanks for the introduction. So in the next roughly 12, 15 minutes, of course, I have to give a brief introduction to Dow, just one slide. A couple of facts around hydrogen production, especially electrolysis-based hydrogen production. We've seen a number of those things in the previous presentation, so I'll keep that brief. And then we're going to go into a real project that we are driving at Dow, which is large scale. I mean, if you talk methanol, it's still small, but we're looking up to 200 to 230,000 tons of e-methanol per year, which in the grand scheme of a methanol plant is small, but for such an undertaking on a renewable basis is pretty big. Within that, we're going to look at the project, some economic evaluations, and then also some of the regulatory hurdles that we face to move this to become a reality. Quick intro on Dow. Dow is a global chemical company. We just merged with DuPont. It was kind of a marriage with a pre-announced divorce. So we're kind of in the top 10 of the chemical companies, roughly $40 billion revenue, 36,000 employees, 109 manufacturing sites around the world, and producing in 31 countries. And I think that's sufficient for this purpose. The reason that we look into methanol is pretty much the competitive advantage that our production site in Stade near Hamburg has. So I put this little marker here. It's right at the about an hour south of Hamburg. It's 550 hectares of chemical plant directly at the River Elbe. Produces about 4 million tons of caustic soda, propylene oxide. Total invest about 3.5 billion euros, 1,100 people, and it has the third largest harbor in Lower Saxony. So why does that qualify us to look into these things? For the most part, it's a real unique situation when it comes to green hydrogen. We produce, it's the largest chlorine electrolysis in Europe, 1.6 million tons of chlorine produced in a saltwater electrolysis. And so as a quote unquote byproduct, we get almost 50,000 tons of hydrogen coming out of our electrolyzers. We converted that into fueling hydrogen-propelled cars, since we talk to politicians quite a bit, and they always struggle to make sense of numbers like 50,000 tons. How much is that? It would be enough to fuel about 200,000 hydrogen-propelled passenger cars once per week. In technical terms, it's the equivalent electrolysis capacity of a PEM or alkaline simple water electrolyzer of roughly 280 megawatts, depending on what efficiency you assume. So when we read all these news articles about somebody wants to build 12 megawatts here and 20 there and 5 there, we already have almost 300 megawatts up and running. And given the current prices of an electrolyzer, that would be a typical investment of 300 to 400 million installed total cost. And then also the power cost, if you run 8,000 hours per year and you assume a moderate price of 60 euros per megawatt hour, that would be about 100 million power cost per year. And we already cover that in our cost because we do produce the chlorine and the soda caustic to sell it, so we can dilute those costs. In addition, to make this hydrogen green, we would have to connect to green power, and luckily we are connected directly to the north-south power link, and the northern German wind and solar power is floating through the site. It's not on this aerial image because it's a bit outdated, but TenneT, the grid operator, is just building a new 380 kilovolts connection point here for us. Again, we are consuming 6 terawatt hours of electrical power per year for the chlorine electrolysis. So we are 1% of the German total power, and that's why we have a direct connection. There's another good byproduct or synergy effect is we consume a lot of salt. The reason the site is built there is because it's built on salt under the underground, and we are operating our own mining operations. So we produce about 1 million cubic meters of salt domes storage space per year. We already use that to store propylene and ethylene, which we use in our current operation, but we could also easily create a hydrogen storage cavern where we could then compensate fluctuating availability of green power, put it into hydrogen, store it underground, and consume it 24/7 in a downstream plant. So lots of good things, and we certainly appreciate the hydrogen economy picking up momentum. We've seen the forecast by the EU where the hydrogen is going to go, and these are the assumed market shares. There's a large portion that is supposed to go into mobility. We think that there is going to be a mix in line with what we heard earlier today of direct hydrogen, but also we think that e-methanol and synthetic fuels in general will play a role in these things. So that's why we kind of do that. One of the questions could be, why do you look into methanol and not other things? And we do look into other things as well. We have done studies on green jet fuel. We've looked into selling the hydrogen for direct reduction in steel making, things like that. But basically what we found is because we also have a gas-fired power plant on the site to supply steam and electricity, we already have a point source of CO2, as was referred to in the previous presentation, which is beneficial. And so if we look into sustainable carbon neutral base chemicals, Dow consumes a lot of methanol in our production paths. And also we found that it's the closest to getting a market outlet that justifies the investment. And I'll explain in a minute why. So the green hydrogen production already happens through saltwater electrolysis. And today, physically, 40% of our power is already green. But we checked, we can turn the entire power consumption of roughly 600 megawatts green with sufficient availability if we work with the power suppliers. There are several projects in this space, as were mentioned earlier, Port of Antwerp, talking about 4 to 8 kilotons. There's Nouryon and Gazoni. They are looking to supply green hydrogen for bio-MCN. CRI was mentioned, the Iceland guys. All these announcements are typically in the range of a couple of thousand tons per year. So bio-MCN supplies also bio-based methanol in their routes. So there's a bit of quantity in the market, but no real sustainable methanol market. And I think it's a bit catch-22. We don't have capacity, so people don't want to use it. And then also there's no real demand. That's why people don't build capacity. One of the reasons is if you look into the production cost of hydrogen, and we saw the slides in the first presentation after lunch, if you compare it to natural gas-based hydrogen, if you go a steam methane reforming route, which is 90% of today's hydrogen is produced that way, basically your CO2 footprint is, it comes directly from the gas, so you have just from the chemistry 1 mole of CO2 per 4 moles of hydrogen, and basically so you have 5.5 tons of CO2 emission per ton of hydrogen, and then the energy input to heat it up is another 4 to 5 tons. So overall you get roughly 10 tons, but the costs are really low. It's 1 to 2 euros depending on your gas price and how much you spend in the infrastructure. On the other hand, if you do water electrolysis to make your hydrogen, and let's assume 75% efficiency, that's kind of what the PEM electrolyzer companies promise. I think it's an optimistic value for now. I don't think that they can guarantee that for the whole cycle. But anyway, let's assume 75%. That means given the energy it takes to split water into hydrogen and oxygen, you need about 53 megawatt hours to make 1 ton of hydrogen. The capex is roughly 1,000 euros per kilowatt installed. Again, if you go to the PEM electrolyzer manufacturers, they're going to give you numbers of 700, but you still need to install and put all the peripherals and hook it up and put it up and running. So we usually calculate with about 1,000 euros per kilowatt, and stack life of a PEM electrolyzer is roughly 50,000 hours, and then you need to restack. There's a couple of other costs, salaries and wages, maintenance, water purification. But if you just kind of add it all up. The benefit is really that you have up to 0 CO2 footprint, depending on what you put in there as a power mix. Realistically, if you take wind power, you still have a few grams of CO2 per kilowatt hour, but significantly less than the traditional power mix. But the costs are then in the range of what we assume currently at 4 to 5 euros per kilo. So here's a quick overview. If you put these different factors together in line with what was shown before, the main cost factor is the electricity. So we put the cost of electricity in euros per megawatt hour on the X scale, and then your resulting hydrogen cost. There's an adder for depreciation, cost of capex, and miscellaneous things. But at the typical range where we are, 5 to 6 cents per kilowatt hour, you see that the resulting cost of 4 to 5 euros per kilo. And there's a lot of promises that the capex will go down. Realistically, economy of scale doesn't really play that well for these technologies as it does for a chemical plant. If you have a pipe and you double it in diameter, you have 2 times the material for the wall, but you get 4 times the throughput. So if you have a volume-driven process, economy of scale works well. For electrolyzers, your capacity is based on the area of your electrodes and the current density. And so scaling it doesn't do that much as it does for others. But anyway, there will be improvements, I'm sure. But internally in Dow, we don't think that the production cost is going to drop significantly. We also don't think that efficiency is going to go up that much, maybe 80-something%, maybe 90, but not much higher. So the main driver is power cost. And there, if you talk to people that give you cost like 2 cents per kilowatt hour in Brazil for renewable, yeah, great. But we need to get it into the grid. We need to get it to the plant. If you build several megawatt electrolyzers, you always have to account for grid fees and things, because I don't think you're going to have the space to set up a complete renewable supply of power next to the plant. So why do we still look into methanol? Just give you a few ideas. Recycling methanol needs climate neutral hydrogen, otherwise the footprint is not good. And just to do the math, and that's why I based everything on kilos here, if you want to produce 1 ton of e-methanol, you need roughly 200 kilos of hydrogen. Stoichiometrically is 190, but a little bit of inefficiency. So for the sake of the experiment here, let's use 200 kilos. If you plug in 4 euros per kilo for the cost of hydrogen, that alone gives you 800 euros per ton, just for the hydrogen fraction. You haven't captured any CO2, you haven't paid any operators to run the plant, you haven't built the plant, you haven't depreciated, so just that gives you a significant cost adder. The capex, as I said, is quite significant for building the electrolyzer. And so for us, with the existing hydrogen production, we can compete very well because it saves significant portions. Shown on the right is the price of fossil methanol for the last 20 years in Western Europe. Just to put the 800 plus into perspective, we've seen numbers anywhere between 150 and 500. More recently, I think the average is in the 300 euro per ton base. Currently, we're at 220 or something. So that's what you're competing with. And if you look at the cost structure of a large-scale industrial production plant, you have about 80% of the total capex going into your hydrogen production. If you break down the cost of recycled methanol or e-methanol, power to methanol, using these numbers, you see that the lower yellow bar, that's your capex for the electrolyzer, and then the power cost is really dominating this. And then you have a bit for CCU, carbon capture and things. But our advantage is we already have the electrolyzer and we can share the power cost between other products like chlorine and caustic. So that's why we look into methanol. So in essence, what we do on the site is we have an existing natural gas plant that takes 600 megawatts of natural gas. We have our chlorine electrolysis that we can switch to green power. And then we would take the CO2 and the hydrogen out of these 2 blocks. And in this project that we're looking at, we would then do CO2 capture. We would use the hydrogen purify and compress it, put it in the methanol synthesis unit and get green methanol that then can serve as base chemical, or it can be a biofuel used in marine trucks, cars, or whatever. A couple of summaries here. We could capture up to 330,000 tons of CO2. which is a pretty large capture unit. We can use up to 45,000 tons of the hydrogen we produce, which is the 280 megawatts, and we can produce over 200,000 tons of CO2-based methanol, which is about 50 times bigger than what CRI has in Iceland. So it is sizable in the e-methanol market. It's still much smaller than the 1.x million tons per year typical fossil methanol plants. We do have significantly lower investments than any other location due to the existing hydrogen. We can save on CapEx and OpEx. And for the environmental impact, we would also avoid 140,000 tons of CO2 that would be generated in addition if you do the traditional SMR route. And we can scale this larger by adding water electrolysis because we do have the power and the power grid connection and the salt domes. So we looked at two capacities using 8 kilotons hydrogen, 58 kilotons CO2, produce 42 kilotons of methanol. That's because the 8 kilotons can be easily freed up in our current integration. We also looked at the full scale, which is then the 210 kilotons. Setup is an amines-based capture unit. We think it's the only technology that's ready now to put it at such large scales, and then a traditional methanol synthesis. We're also looking in alternative capture technologies, water-based, enzyme-based, but none of those are ready to invest at this scale at this point. We've gotten budget quotes for all these units from the technology leaders, competing budget offers from different suppliers for all the units involved. So we have a fair understanding what the capital cost is to build this thing. And to summarize, the production of green methanol from green hydrogen and CO2 is significantly cost disadvantaged versus fossil. Even with an ideal setup like we have in Douwstade, where we have the hydrogen at very moderate prices, we can't compete, but we get close. And so there has been discussion with several potential downstream market players. Marine fuel has been presented, and one of the issues there is that you need 50% more because the heat value is lower. So if you come with a higher price, their fuel costs go through the roof. This is only suitable for cruise industry. Cars, trucks is one, and chemical use is the one where we have the best return because the cost portion of the end product is the smallest, so they can afford to do that. A couple of things need to happen to make this a reality. RED 2, the Renewable Energy Directive 2, would be a great way to reduce the hurdle there because we could reach cost recovery. CapEx funding is something that the German government is looking into. Also, important projects of common European interest is the funding mechanism. CO2 penalties are unlikely to compensate that. If you think about the 1 ton difference, you would need about 800 tons per ton CO2, 800 euros. One hurdle is carbon capture and use is currently not accepted under the ETS, so we would still have to pay our emissions. And we hope that the end consumer ultimately is going to pay a higher price for green products, which would enable that. So in summary, we are ready to invest. We are getting close. We have a combination of subsidies lined up. We have some early movers, large brand owners who are willing to pay a premium in the chemical use area. And we are currently signing the contracts to have strategic partnerships to spread the risk over multiple players. But it is a difficult business, even though we are uniquely advantaged. Thanks.
Thanks a lot, Jens. I'll follow that up with a question immediately linking to some of the challenges that you just listed up. Question on whether it really is green methanol if you use CO2 from a fossil gas source.
Yeah, we've clarified that with the, first of all, there's a couple of different things in the market. If you do a life cycle analysis, it counts as avoided CO2. Mm-hmm. If you really want to be green, then you could also switch to biogas going into your gas-fired power plant, and then you would have bio-based CO2. But from what we learned from our brand owners and off-takers, they would be okay with using the point source of a fossil plant because it's not built for that purpose, it's already there. So we basically avoid the emissions.
Great. Then I would suggest that we keep the other questions for the Q&A session so that we stick to the schedule. Thanks again, and we'll get back to you soon.